15 billion miles from Earth, a machine built in 1977 is dying. Its power supply, 3 canisters of decaying plutonium-238, is generating less electricity every year. Its cameras have been dark since 1990. Its instruments are shutting down one by one, each sacrifice buying a few more watts, a few more months of contact. Right now, Voyager 1 has about 220 watts of power left. That's less than 3 standard light bulbs, and with that it's running a transmitter, a heater, a magnetometer, a cosmic ray detector, and the attitude control system that keeps its antenna pointed at a pale blue dot it left nearly half a century ago. A signal from Voyager 1 takes over 22 hours to reach Earth. When NASA sends a command, the engineers wait 22 hours for it to arrive, then another 22 hours for the response. A single conversation takes nearly 2 days. You can't troubleshoot in real time, you can't react to problems. You send a command and you wait, hoping the spacecraft you built before the invention of the personal computer understood what you meant. And yet, despite all of this, Voyager 1 is still transmitting, still sending data from a place no human-made object has ever been. A place beyond the solar wind, beyond the sun's magnetic bubble, beyond everything we've ever known. Interstellar space, the void between stars. And what it's found there has rewritten our understanding of where the solar system ends and what lies beyond. But before it got there, it had to cross something nobody expected. A wall of superheated particles burning at temperatures up to 50,000 Kelvin. That's roughly 90,000 degrees Fahrenheit, 9 times hotter than the surface of the sun, hot enough to vaporize steel, titanium, tungsten, any material known to human engineering. Scientists call it the Wall of Fire, and Voyager sailed straight through it. Let's start at the beginning. On September 5, 1977, a Titan IIe rocket lifted off from Cape Canaveral, Florida, carrying Voyager 1 into the sky. 16 days earlier, on August 20th, its twin, Voyager 2, had already launched. The numbering is confusing because Voyager 1, despite launching second, was on a faster trajectory that would allow it to reach Jupiter first. The names refer to the order of arrival, not launch. The Voyager program was designed to exploit a rare planetary alignment that occurs roughly once every 176 years. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were arranged in a configuration that allowed a single spacecraft to visit all 4 using gravity assists, using each planet's gravitational pull to slingshot to the next. This alignment, called the Grand Tour, was a once-in-a-lifetime opportunity. Literally, no one alive when the mission was planned would live to see the next alignment. The original mission plan was modest. Voyager 1 would fly by Jupiter and Saturn. Voyager 2 would fly by Jupiter, Saturn, Uranus, and Neptune. The primary mission was scheduled to last 4 years, maybe 5 if they were lucky. The budget was tight, the technology was limited. The computers on board Voyager had about 69 kilobytes of memory. Your smartphone has roughly 1 million times more. The spacecraft's main computer could execute about 8,000 instructions per second. A modern laptop executes billions. But the engineering was extraordinary. The spacecraft bus, the central body of the probe, is roughly the size of a small car. It's made of aluminum and is remarkably light, about 825 kilograms fully fueled. Mounted on the bus is a 3.7-meter high-gain antenna, the large white dish that dominates most photographs of the spacecraft. This antenna must point directly at Earth for the signal to be received. If it drifts even a fraction of a degree, communication is lost. Power comes from 3 radioisotope thermoelectric generators, or RTGs, mounted on a boom extending from the spacecraft body. Each RTG contains pellets of plutonium-238, which decays radioactively, producing heat. Thermocouples convert that heat into electricity. It's a simple, reliable system with no moving parts, which is why it's lasted so long. but plutonium-238 has a half-life of 87.7 years. Every year, the RTGs produce slightly less heat and therefore slightly less electricity. When Voyager launched, the 3 RTGs produced about 470 watts. Today, they produce about 220, and the decline continues at about 4 watts per year. When the power drops below the threshold needed to run the transmitter, Voyager goes silent. The spacecraft carries 11 scientific instruments, though most are now turned off. The cameras, part of the imaging science subsystem, produce some of the most iconic photographs in the history of space exploration. The first close-up images of Jupiter's Great Red Spot, the discovery of active volcanoes on Io. The first detailed views of Saturn's rings, the discovery of geysers on Triton, and, on February 14, 1990, at Carl Sagan's suggestion, the famous pale blue dot photograph, an image of Earth taken from 6 billion kilometers away, in which our planet appears as a tiny speck of light suspended in a sunbeam. After that photograph, the cameras were turned off forever. There was nothing left to photograph. Ahead was only darkness. Let's follow Voyager 1's path through the solar system, because understanding where it's been helps us understand the significance of where it is now. Voyager 1 reached Jupiter on March 5, 1979, passing within 349,000 kilometers of the cloud tops. It was not the first spacecraft to visit Jupiter. Pioneers 10 and 11 had flown by in 1973 and 1974. But Voyager carried far better cameras and instruments, and what it found was revelatory. Jupiter is the largest planet in the solar system, a gas giant with a mass 318 times that of Earth and a diameter 11 times wider. Its atmosphere is mostly hydrogen and helium, banded with clouds of ammonia, water, and ammonium hydrosulfide, driven by winds reaching 640 kilometers per hour. The Great Red Spot, a storm large enough to swallow Earth, had been observed through telescopes for centuries. But Voyager revealed it in stunning detail, a churning anticyclonic vortex with complex internal structure, smaller storms being absorbed at its edges, and cloud features that changed visibly from day to day. But the biggest discoveries came from Jupiter's moons. Voyager 1 flew past Io, the innermost of the 4 large Galilean satellites, and found something nobody had predicted: volcanoes. Active, erupting volcanoes. Io's surface was covered with them, more than 400, some shooting plumes of sulfur and sulfur dioxide hundreds of kilometers above the surface. Io was the most volcanically active body in the solar system, more active than Earth, and nobody had known until Voyager flew past. The volcanism was driven by tidal heating. Jupiter's enormous gravity, combined with the gravitational tugs of Europa and Ganymede, flexes Io's interior, generating friction and heat. The same process that would later be recognized as the mechanism keeping Europa's subsurface ocean liquid was, on Io, generating enough heat to melt rock. Io's surface is continuously being resurfaced by lava flows and volcanic deposits so rapidly that impact craters, which should be ubiquitous on any airless body, are virtually absent. The surface is young, geologically speaking, always being remade. Voyager also took the first close-up images of Europa, revealing an ice surface crisscrossed with fractures and remarkably smooth, almost devoid of craters. The smoothness suggested that the surface was being renewed, possibly by liquid water welling up from below. This was the first hint of what would later be confirmed. Europa has a global ocean of liquid water beneath its ice shell, kept liquid by tidal heating, possibly containing more water than all of Earth's oceans combined. After Jupiter, Voyager 1 used the planet's gravity to slingshot towards Saturn, arriving on November 12, 1980. It passed within 124,000 kilometers of Saturn's cloud tops, studying the planet's atmosphere, rings, and moons. Saturn's rings had been known since Galileo first observed the planet in 1610, though he couldn't resolve them clearly enough to understand what he was seeing. He thought Saturn had ears, It wasn't until 1655 that Christian Huygens correctly identified the structure as a flat ring surrounding the planet. Ground-based telescopes had identified several broad divisions in the rings, including the prominent Cassini division, a dark gap between the A and B rings. Voyager revealed the rings in astonishing complexity. What had appeared as a few broad bands resolved into thousands of individual ringlets, some of them braided, kinked, or exhibiting spokes, dark radial features that appeared and disappeared over hours. The rings were made of billions of particles, from tiny grains of ice to house-sized boulders, all orbiting Saturn in a vast, thin disk. The rings extend hundreds of thousands of kilometers from the planet, but are typically only about 10 meters thick. The ratio of width to thickness is staggering. If you shrunk the rings to the diameter of a football field, they would be thousands of times thinner than a sheet of paper. But Voyager 1's most consequential encounter at Saturn was with Titan, Saturn's largest moon. Titan was known to have a thick atmosphere, the only moon in the solar system to possess one. Voyager's mission planners decided to send the spacecraft on a trajectory that would allow a close flyby of Titan, passing within 6,490 kilometers of the surface. This trajectory came with a cost. It would fling Voyager 1 out of the plane of the solar system, making it impossible to continue to Uranus and Neptune. The grand tour for Voyager 1 ended at Saturn. Only Voyager 2 would complete the full journey to all 4 outer planets. The Titan flyby revealed a world shrouded in a dense, opaque orange haze. Voyager's cameras couldn't see the surface at all. The atmosphere was found to be mostly nitrogen, like Earth's, but much thicker, with a surface pressure about 1.5 times Earth's. The temperature at the surface was about -179 degrees Celsius, cold enough for methane to exist as a liquid. Scientists speculated that Titan might have lakes or oceans of liquid hydrocarbons, a prediction that would be spectacularly confirmed decades later by the Cassini-Huygens mission. After Saturn, Voyager 1 was heading up and out of the solar system. Its planetary mission was over, but its greatest discoveries were still decades away. Voyager 2, meanwhile, continued the grand tour. It reached Uranus on January 24, 1986, the first and so far only spacecraft to visit this ice giant. Uranus is a deeply strange world. It rotates on its side with an axial tilt of 98 degrees, so extreme that it essentially rolls around its orbit like a bowling ball. This tilt is probably the result of a catastrophic collision with an Earth-sized body early in the solar system's history. Voyager 2 found a bland, featureless blue-green disk with very little visible atmospheric structure, masking powerful winds and a complex interior. It also discovered 10 new moons and 2 new rings. On August 25, 1989, Voyager 2 made its closest approach to Neptune, the last stop on the grand tour. Neptune was a revelation. Despite receiving almost no energy from the distant sun, the planet had the fastest winds in the solar system, gusting up to 2,100 kilometers per hour. It had a great dark spot, an Earth-sized storm system that appeared and disappeared over the following years. And its largest moon, Triton, was one of the most extraordinary worlds Voyager encountered anywhere. Triton orbits Neptune backwards in the opposite direction to the planet's rotation, strong evidence that it was captured from the Kuiper belt rather than forming in place. Its surface temperature is about -235 degrees Celsius, making it one of the coldest known objects in the solar system. Despite this extreme cold, Voyager found active geysers on Triton, plumes of nitrogen gas erupting from beneath the surface and rising 8 kilometers into the thin atmosphere before being blown sideways by high-altitude winds, leaving dark streaks on the icy surface. Geysers on a world at -235 degrees. The solar system Voyager taught us is stranger than anyone imagined. After Neptune, Voyager 2, like its twin, headed for the outer reaches of the solar system. Both spacecraft were now on escape trajectories, moving fast enough to overcome the sun's gravity and leave the solar system forever. The planetary missions were over. The interstellar missions were beginning through the 1990s and 2000s. Both Voyagers continued to return data from the outer solar system. The instruments that could still operate in the cold darkness beyond the planets measured the solar wind, magnetic fields, cosmic ray intensities, and plasma wave. The probes were traversing a region of space no instrument had ever sampled, and what they found was a slow, subtle drama playing out at the farthest reaches of the Sun's influence. To understand what Voyager encountered, we need to understand the heliosphere. The Sun doesn't just emit light and heat, it blows continuously. In all directions, it sends out a stream of charged particles, mostly protons and electrons, moving at speeds of 300 to 800 kilometers per second. This is the solar wind. It is not wind in the terrestrial sense. There is no air. It is a flow of plasma, ionized gas, streaming outward from the Sun's corona at supersonic speeds, carrying the Sun's magnetic field with it. The solar wind fills an enormous volume of space, inflating a magnetic bubble around the Sun called the heliosphere. This bubble extends far beyond the orbits of all the planets, out past the Kuiper belt to a distance of roughly 18 billion kilometers from the Sun, 120 astronomical units or so, depending on direction and solar activity. Inside this bubble, the dominant electromagnetic environment is controlled by the Sun. The magnetic field is the Sun's field, stretched and twisted by the solar wind's rotation. The particle population is dominated by solar wind particles. It is, in a very real sense, the Sun's domain, the Sun's territory. But the solar wind doesn't blow forever. It can't. The Sun is moving through the galaxy, and the galaxy is not empty. The space between stars contains the interstellar medium, a thin but measurable population of gas, mostly hydrogen and helium, along with dust, plasma, cosmic rays, and magnetic fields. The interstellar medium has its own pressure, its own magnetic field, its own momentum. And when the solar wind encounters this medium, it has to slow down, compress, heat up, and eventually stop. The boundary where the solar wind's outward pressure equals the inward pressure of the interstellar medium is the heliopause. It is the outer edge of the heliosphere, the true boundary of the Sun's influence. Beyond it, the interstellar medium rules. But the transition isn't simple. It happens in stages, across a series of boundaries, each with its own characteristics. The first boundary is the termination shock. This is the point where the solar wind drops from supersonic to subsonic speed, like a jet aircraft crossing the sound barrier in reverse. The solar wind decelerates abruptly, heating up and compressing as it does so. The termination shock is not at a fixed distance, it fluctuates with solar activity, moving outward when the solar wind is strong and inward when it weakens. Voyager 1 crossed the termination shock on December 16, 2004, at a distance of about 94 astronomical units, roughly 14 billion kilometers from the Sun. Voyager 2 crossed it on August 30, 2007, at about 84 astronomical units, 10 ALUN closer. The difference was partly due to asymmetries in the heliosphere and partly due to changes in solar activity between the two crossings. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind is compressed and heated, piling up against the interstellar medium like water backing up behind a dam. The heliosheath is thick, extending billions of kilometers. Conditions inside it are chaotic. Magnetic fields twist and fold. Particles bounce back and forth. Temperatures rise. The solar wind, no longer supersonic, becomes a hot, disordered plasma, struggling against the inward pressure of the galaxy. And beyond the heliosheath lies the heliopause. The wall, the edge. Voyager 1 crossed the heliopause on August 25, 2012. The date was not known immediately. Data transmission is slow and the signals are faint. NASA scientists spent months analyzing the data before they were confident enough to announce it. On September 12, 2013, More than a year after the crossing, NASA officially confirmed that Voyager 1 had entered interstellar space. How did they know? Three things changed. First, the density of solar wind particles dropped to near zero. Inside the heliosphere, the solar wind dominates the particle environment. The detectors were measuring solar wind particles at every sampling interval. Then, abruptly, they stopped. The solar wind was gone. Voyager had crossed out of the sun's bubble. Second, cosmic ray intensity jumped. Cosmic rays are high-energy particles, mostly protons, accelerated to near light speeds by supernovae and other violent cosmic events. Inside the heliosphere, the sun's magnetic field deflects many of these particles, providing partial shielding. Outside, there's no shield. Cosmic rays pour in from all directions, unimpeded. Voyager's cosmic ray detector recorded a sharp increase in the galactic cosmic ray flux. At the same time, the solar wind disappeared. The probe had crossed from a shielded environment into an unshielded one. Third, the plasma density changed. Voyager 1's plasma instrument had stopped working in 1980, but the plasma wave subsystem could still infer the density of the surrounding plasma by measuring the frequency of plasma oscillations, vibrations in the electron density triggered by solar events. The oscillations indicated a dramatic increase in plasma density, consistent with the transition from the thin solar wind plasma to the denser interstellar medium. The interstellar medium, while incredibly sparse by terrestrial standards, is denser than the solar wind at that distance. These three measurements, solar wind particles dropping to zero, cosmic rays jumping up, plasma density increasing, told the same story. Voyager 1 had left the heliosphere. Voyager 2 followed 6 years later, crossing the heliopause on November 5, 2018, at a distance of about 119 astronomical units. Voyager 2's crossing was in some ways more scientifically valuable because its plasma instrument was still working. It provided direct measurements of the plasma properties on both sides of the boundary, data that Voyager 1 could not collect. The measurements revealed that the heliopause is remarkably thin, a transition layer perhaps 1 to 2 astronomical units across, where conditions change rapidly from solar-dominated to interstellar-dominated. Now let's talk about the wall of fire, because the temperatures that Voyager measured in the boundary region are genuinely extraordinary, and understanding why they exist and why they didn't destroy the spacecraft reveals something fundamental about the nature of space. The heliosheath, the region between the termination shock and the heliopause, is hot. Extremely hot. Temperatures in this region reach 30,000 to 50,000 Kelvin. In Fahrenheit, that's 54,000 to 90,000 degrees. The surface of the Sun is about 5,800 Kelvin, roughly 10,000 degrees Fahrenheit. So the heliosheath is, in terms of particle temperature, considerably hotter than the surface of the Sun. When Voyager 1's instruments first measured these temperatures, NASA scientists were stunned. The data was checked and rechecked. The instruments were functioning correctly. The readings were real. The particles in the heliosheath were genuinely superheated, far hotter than anything the spacecraft was designed to withstand. And yet, Voyager didn't melt. It didn't degrade. Its instruments continued to function perfectly. The spacecraft sailed through a region hotter than the surface of the Sun, as if it were passing through a gentle breeze. The explanation lies in the distinction between temperature and heat, two concepts that sound interchangeable in everyday language, but are fundamentally different in physics. Temperature is a measure of the average kinetic energy of particles. When particles move fast, the temperature is high. When they move slowly, the temperature is low. In the heliosheath, the particles are moving extraordinarily fast, giving them very high temperatures. But here's the crucial point. Temperature tells you about the speed of individual particles. It tells you nothing about how many particles there are. Heat transfer, the actual flow of thermal energy from one object to another, depends not just on the temperature of the particles, but on their density. How many particles are hitting the spacecraft per second? In the heliosheath, the density is staggeringly low. We're talking about perhaps 0.001 particles per cubic centimeter in some regions. For comparison, the air you're breathing right now has about 25 quintillion molecules per cubic centimeter. 25 followed by 18 zeros. The heliosheath has less than 1 particle per 1,000 cubic centimeters. So while each individual particle carries enormous kinetic energy, the number of particles actually hitting the spacecraft at any given moment is vanishingly small. The total energy transferred to Voyager is negligible. It's like standing in a room where a bullet is fired once every 1,000 years. Each bullet carries a lot of energy, but you'll never be hit. Think of it another way. Stick your hand in a 200-degree oven and you'll feel hot, but you won't burn immediately because air is a poor conductor of heat, and the density of air molecules touching your skin at any given moment is relatively low. Now stick your hand in 200-degree water and you'll burn instantly, because water is much denser and transfers heat far more effectively. The heliosheath is like an oven at 90,000 degrees, but with 1,000,000 trillion times less air. Each molecule is furiously hot, but there are so few of them that they can barely touch you. This distinction between temperature and heat is one of the most counterintuitive facts in physics, and it's why Voyager survived the wall of fire. But just because Voyager wasn't melted doesn't mean the crossing was benign. The real danger wasn't thermal, it was electromagnetic. The heliosheath and heliopause are regions of intense magnetic turbulence. Solar magnetic field lines, stretched and twisted by billions of kilometers of travel, pile up against the interstellar magnetic field. The two fields interact, tangle, reconnect. Magnetic reconnection is one of the most violent processes in plasma physics. When field lines break and rejoin in a different configuration, they release enormous amounts of energy, flinging particles to high speeds in random directions. In the heliosheath, this is happening constantly, creating a chaotic magnetic environment that buffets any object passing through it. Voyager 1's magnetometer recorded extraordinary fluctuations during the crossing. The magnetic field strength spiked and plummeted erratically. The field direction reversed, polarity flipped. For weeks, the data looked like noise. NASA engineers initially wondered if the instrument was malfunctioning. It wasn't. The readings were real. The heliopause was simply that turbulent. These magnetic fluctuations have real consequences. Charged particles spiral along magnetic field lines. When those field lines are chaotic and rapidly changing, the particles are accelerated to high energies, producing intense localized radiation. Some of these particles reach energies of hundreds of millions of electron volts, enough to penetrate the spacecraft's thin aluminum hull and strike sensitive electronic components inside. A single high-energy particle striking a memory chip can flip a bit, changing a 0 to a 1 or vice versa. This is called a single event upset, and it can corrupt data, trigger false commands, or temporarily disable systems. Voyager's engineers anticipated this problem, at least in general terms. Critical systems have redundancy. Memory is error-checked. Software routines detect and correct bit flips. But the engineers in 1977 didn't know about the heliopause or the magnetic violence that awaited. The fact that Voyager's systems have withstood decades of cosmic ray bombardment, including the intensified radiation of the heliopause crossing, is a testament to the robustness of the engineering and a fair measure of luck. 6 years after Voyager 1, Voyager 2 crossed the heliopause at a different location. Voyager 1 crossed roughly in the direction the solar system is moving through the galaxy, the nose of the heliosphere, where the boundary is compressed and closer to the Sun. Voyager 2 crossed in a different direction, toward the flank of the heliosphere, where the boundary is farther out and shaped differently. Voyager 2's crossing confirmed several of Voyager 1's findings. The temperature spike was real, the magnetic turbulence was real. The sharp transition from solar-dominated to interstellar-dominated plasma was real. But Voyager 2 also found differences. The magnetic field direction on the interstellar side was slightly different at Voyager 2's crossing point. The plasma density profile was different. The width of the transition zone was different. The heliopause these data showed is not uniform. It varies from place to place, shaped by local conditions in both the solar wind and the interstellar medium. And Voyager 2 found something that surprised everyone. The magnetic field in interstellar space, just beyond the heliopause, was aligned roughly parallel to the magnetic field just inside the heliosphere. Scientists had expected a sharp change in field direction at the boundary, like crossing from one country to another where they drive on the other side of the road. Instead, the field was smooth, continuous, as if the transition didn't really change the magnetic landscape at all. This was puzzling. The solar magnetic field and the interstellar magnetic field have different origins. The solar field is generated by the sun's internal dynamo and carried outward by the solar wind. The interstellar field is generated by the galactic dynamo by the collective motion of charged particles throughout the Milky Way. These two fields shouldn't be aligned. Finding them parallel at the heliopause was like finding two rivers from different mountain ranges flowing side by side in exactly the same direction. It suggests either that the interstellar field has structure and direction that happens to match the solar field at this particular point, or that the two fields are somehow connected across the boundary, coupled by plasma processes we don't fully understand. This discovery has profound implications. If the solar magnetic field connects to the interstellar field, the heliosphere is not the impermeable bubble we imagined. It's more like a membrane. Some things pass through, magnetic field lines, certain particles. Others are blocked. The bulk solar wind, lower energy charged particles. The boundary is selective, permeable, dynamic. It's not a wall, it's an interface. Let's talk about what the heliosphere actually looks like. For decades, the textbook picture was a neat sphere, like a soap bubble, with the sun at the center. This picture was always understood to be simplified, but the general assumption was that the heliosphere was roughly spherical, perhaps slightly elongated in the direction of the sun's motion through the galaxy. Voyager's data, combined with observations from other missions, has revealed a much more complex picture. The heliosphere is shaped like a comet, or more precisely, like a blunt bullet. The front, facing the direction of the solar system's motion through the interstellar medium, is compressed. The back is stretched into a long tail, called the heliotail, that extends billions of kilometers behind the solar system. This shape is created by the interaction between the solar wind and the interstellar medium. The solar system is moving through the galaxy at about 230 kilometers per second, approximately 828,000 kilometers per hour. As it plows through the interstellar medium, the front of the heliosphere is compressed, while the back is stretched by the flow of the interstellar medium around and behind it. Think of a boat moving through water. The bow creates a wave where the boat's momentum meets the water's resistance. Behind the boat, a wake forms. The heliosphere is like the boat. The interstellar medium is like the water. But it might be even stranger than that. Some models suggest the heliosphere doesn't have a tail at all. In 2015, a team of scientists proposed that the heliosphere might be shaped more like a crescent or a deflated croissant, with two jets of solar wind flowing off the back instead of a single tail. Other models suggest a rounder shape, more like a sphere with two slightly elongated lobes. The truth is, we've only sampled the heliosphere at 2 points, the locations where Voyager 1 and Voyager 2 crossed. We're trying to determine the shape of an enormous three-dimensional structure from just 2 data points. It's like trying to determine the shape of Africa by visiting 2 cities. NASA's Interstellar Boundary Explorer mission, IBEX, has helped by mapping the heliosphere from the inside using a technique called energetic neutral atom imaging. IBEX detects neutral atoms that have been created at the heliosphere's boundary and travel back toward the inner solar system by mapping the directions and energies of these atoms. IBEX has produced images of the heliopause that suggest it's not a simple smooth surface, but a complex dynamic multi-layered structure that changes shape over time. And the heliosphere breathes. The Sun goes through an 11-year activity cycle. At solar maximum, sunspots are abundant. Solar flares erupt frequently, and the solar wind blows harder and faster. At solar minimum, the Sun is quieter, and the solar wind weakens. These fluctuations cause the heliosphere to expand and contract. The heliopause pushing outward during solar maximum and retreating inward during solar minimum. The total displacement might be hundreds of millions of kilometers. The heliosphere pulses like a living thing, responding to the heartbeat of the Sun. Coronal mass ejections, enormous eruptions of plasma from the Sun's corona, create additional disturbances. A single CME can eject billions of tons of magnetized plasma at speeds of up to 3,000 kilometers per second. When this wave of plasma reaches the heliosheath, it creates a pressure pulse that propagates outward through the boundary. One such pulse, triggered by a series of CMEs in 2012, reached Voyager 1 13 months later, causing a temporary doubling of the plasma density around the spacecraft. These events demonstrate that the Sun's influence can reach deep into interstellar space, even beyond the heliopause. Just before Voyager 1 crossed the heliopause, it entered a region that baffled scientists. They called it the magnetic highway. In this zone, which extended for about 1 to 2 astronomical units just inside the heliopause, the magnetic field lines from the Sun connected with field lines from the interstellar medium, creating pathways along which particles could flow in both directions. Solar particles streamed outward along these field lines into interstellar space, while galactic cosmic rays flowed inward into the heliosphere. It was as if the boundary had become porous, allowing a two-way exchange of particles. This was completely unexpected. Scientists had predicted a clean transition, a sharp boundary where solar conditions ended and interstellar conditions began. Instead, they found a transition zone where the two regimes mixed and interacted. Particles from inside the heliosphere and particles from outside coexisted, flowing along shared magnetic field lines. The magnetic highway changed everything about how scientists understand the heliopause. It's not a wall. It's not even a simple boundary. It's a complex dynamic interface where two cosmic environments negotiate. Now let's cross the heliopause ourselves and enter interstellar space. The first thing Voyager found beyond the heliopause is that interstellar space is not empty. We imagine the space between stars as a perfect vacuum, an absolute void. It's not. It's filled with the interstellar medium, a thin but measurable population of gas, dust, plasma, cosmic rays, and magnetic fields. The density is low by any terrestrial standard. The interstellar medium near the Sun contains roughly 0.1 to 0.3 atoms per cubic centimeter. Compare that to Earth's atmosphere at sea level, about 25 million trillion atoms per cubic centimeter. Interstellar space is empty by our standards, but it's not nothing. Those atoms matter. The gas is mostly hydrogen, about 70% by mass, with about 28% helium and about 2% heavier elements. The astrophysical definition of metals, which includes everything heavier than helium. This gas is the raw material from which stars form. It's left over from the Big Bang, mixed with material that has been processed through stars and returned to the interstellar medium through stellar winds and supernova explosions. Every heavy atom in the interstellar medium was manufactured inside a star. The carbon, oxygen, silicon, iron, all of it was forged by nuclear fusion and scattered into space when stars died. The gas exists in several phases. There's cold neutral gas with temperatures of about 50 to 100 Kelvin, forming dense clouds. There's warm neutral gas at about 6,000 to 10,000 Kelvin, filling much of the volume between the clouds. There's warm ionized gas at similar temperatures, but with its atoms stripped of electrons, and there's hot ionized gas at temperatures of millions of Kelvin, created by supernova explosions that blast enormous bubbles of superheated plasma into the interstellar medium. Voyager 1 is currently passing through a region called the local interstellar cloud, a relatively warm, partially ionized cloud of gas about 30 light-years across. The local interstellar cloud has a temperature of about 7,000 Kelvin and a density of about 0.3 atoms per cubic centimeter. It's heated by ultraviolet radiation from nearby hot stars and by shock waves from relatively recent supernovae. The local interstellar cloud is itself embedded in a much larger and much emptier structure called the local bubble, a cavity in the interstellar medium about 300 light-years across that was created by a series of supernova explosions over the past 10 to 20 million years. The explosions swept the gas outward, creating a low-density bubble of hot, thin plasma surrounded by a shell of denser material. The Sun entered the local bubble a few million years ago and is currently near its center. In a few thousand years, the Sun will exit the local interstellar cloud and may enter a different region of the local bubble with different density and temperature characteristics. If the density of the local interstellar medium changes significantly, the heliosphere will respond. It could compress, shrink, change shape. The wall of fire could intensify or diminish. The radiation environment of the outer solar system could change. This is not an academic concern. The heliosphere is our shield. It deflects a significant fraction of galactic cosmic rays, protecting the inner planets. If the heliosphere shrinks, because the external pressure increases, more cosmic rays reach Earth. Studies of isotope ratios in ancient sediments suggest that cosmic ray flux at Earth has varied over geological time, possibly in response to changes in the local interstellar medium as the solar system moves through different regions of the galaxy. Some researchers have speculated about links between cosmic ray variations and climate change, mass extinctions, or other biological effects. The evidence for these links is debated and far from conclusive, but the basic physics is clear. The heliosphere matters, it protects us, and it can change. Let's talk about cosmic rays, because they are one of the most important things Voyager has measured in interstellar space, and one of the biggest obstacles to future human exploration beyond the heliosphere. Cosmic rays are not rays at all. They are particles, mostly protons, but also helium nuclei, heavier atomic nuclei, and electrons, traveling at speeds approaching the speed of light. Their energies are staggering. A single cosmic ray proton can carry as much kinetic energy as a baseball thrown by a professional pitcher. That energy is concentrated in a single subatomic particle. Cosmic rays come from outside the solar system. Most are produced by supernova explosions. When a massive star explodes, it releases about 10 to the 44th joules of energy, roughly the total energy output of the Sun over its entire 10 billion year lifetime, released in a few seconds. Some of that energy goes into accelerating particles to near-light speeds. These particles then travel through the galaxy for millions of years, bouncing off magnetic fields, spiraling along field lines, gradually diffusing through the interstellar medium until they reach the solar system. Inside the heliosphere, the Sun's magnetic field provides partial shielding against cosmic rays. The field deflects lower energy cosmic rays, bending their trajectories away from the inner solar system. Higher energy cosmic rays can penetrate the shield, but their flux is reduced. The heliosphere doesn't block all cosmic rays, but it significantly reduces their intensity. Outside the heliosphere, there's no shield. Voyager 1's cosmic ray detector recorded a sharp increase in galactic cosmic ray flux upon crossing the heliopause. The increase was about 12% for the highest energy particles, and much larger for lower energy particles that had been more effectively shielded inside the heliosphere. In interstellar space, cosmic rays arrive from all directions, unimpeded, at their full galactic intensity. This is a serious problem for any future mission to interstellar space. Cosmic rays are intensely damaging to biological tissue. When a high-energy particle passes through the human body, it ionizes atoms along its path, breaking chemical bonds, damaging DNA, and creating reactive chemical species that cause further damage. A single heavy cosmic ray nucleus can produce a track of ionization that destroys thousands of cells along its path. Cumulative exposure increases cancer risk, damages the central nervous system, and can cause acute radiation sickness at high doses. Astronauts in low Earth orbit are partially protected by Earth's magnetic field and atmosphere. Astronauts on the International Space Station receive about 150 millisieverts of radiation per year, roughly 60 times the dose received by the average person on Earth's surface. Astronauts on a Mars mission outside Earth's magnetosphere for months would receive even more. Astronauts beyond the heliopause would receive substantially higher doses still, with no natural shielding at all. Current spacecraft shielding is inadequate for interstellar radiation levels. Aluminum, the most common spacecraft material, actually makes the problem worse. When a high-energy cosmic ray strikes an aluminum nucleus, it fragments both, creating a shower of secondary particles that increases the total radiation dose inside the spacecraft. This is called spallation, and it means that adding more aluminum can paradoxically increase the radiation exposure. Better shielding materials exist. Polyethylene, a hydrogen-rich plastic, is much more effective at absorbing cosmic ray energy because hydrogen nuclei, being the lightest, absorb energy in collisions more efficiently without producing as many secondary particles. Water works well too, for similar reasons. Some designs propose surrounding crew quarters with thick layers of water, which would serve triple duty as radiation shielding, life support reserve, and thermal mass. But the best solution would be active shielding, generating a magnetic field around the spacecraft strong enough to deflect incoming cosmic rays, mimicking the protection provided by Earth's magnetosphere. This is technically conceivable, but enormously challenging. The magnetic field would need to be strong enough to deflect particles moving at 90% the speed of light or more. That requires superconducting magnets of enormous size, consuming significant power. Current technology isn't close, but the concept is being studied. Until the radiation problem is solved, human travel beyond the heliosphere remains, in practical terms, impossible. Voyager can survive because it's a machine. It doesn't get cancer. It doesn't suffer neurological damage. A cosmic ray that flips a bit in its memory is an annoyance that can be corrected by error-checking software. The same particle passing through a human brain is something else entirely. Now let's talk about the future. Voyager 1 is dying, and there's no way to stop it. The plutonium-238 in its RTGs has been decaying for nearly 50 years. The power output drops by about 4 watts per year. At current rates, Voyager 1 will cross the critical threshold, the minimum power needed to keep the transmitter and at least one instrument running sometime between 2025 and 2030. NASA engineers have been managing the decline with extraordinary creativity. They've shut down every non-essential system. The cameras went dark in 1990. The ultraviolet spectrometer in 2003. The plasma wave subsystems data collection has been reduced. Heaters for fuel lines have been turned off, allowing the hydrazine propellant to approach its freezing point. In 2023, NASA engineers faced a particularly dramatic challenge. The primary attitude control thrusters, the small rockets that keep Voyager's antenna pointed at Earth, were degrading. They were clogging with propellant residue after decades of use. Without functioning thrusters, the antenna would drift out of alignment and contact would be lost permanently. The backup thrusters hadn't been fired since 1980 during the Saturn encounter. They were designed for planetary flybys, not for fine attitude control. The engineers dug through archived documentation from the 1970s, some of it on paper, to understand how the backup thrusters work. They wrote new software to control them, uploaded it to a spacecraft 15 billion miles away over a signal that takes 22 hours each way, and fired the thrusters for the first time in 43 years. They worked. Voyager 1 stabilized. The mission continued, but these fixes are temporary. The power decline is relentless and irreversible. Every year, fewer watts are available. Every year, another system or instrument may need to be sacrificed. The engineering team, many of whom inherited the mission from the original designers, now faces the most difficult decisions of the mission. Which instruments stay on? Which get shut down? How do you maximize the scientific return from a spacecraft's final years of life? The magnetometer is the leading candidate to be the last instrument standing. It measures magnetic fields, and it's providing data that no other instrument anywhere can provide. No other spacecraft has crossed the heliopause. No other mission to interstellar space is planned for at least another decade. If the magnetometer shuts down, humanity loses its only eye on the magnetic environment of interstellar space, the environment that shapes cosmic ray propagation, star formation, and galactic structure on the largest scales. The cosmic ray subsystem is also scientifically invaluable. It's been measuring the galactic cosmic ray flux continuously as Voyager moves deeper into interstellar space, building a profile of how cosmic rays behave far from the heliosphere's influence. This data is crucial for understanding radiation hazards for future interstellar missions. But keeping both instruments running may not be possible as power declines. At some point, probably within the next few years, the final instrument will go dark, the transmitter will lose power, and the last signal will fade into the noise. NASA's Deep Space Network, the array of massive dish antennas that receives Voyager's transmissions, will listen for a while longer, just in case. Then, eventually, the antennas will be redirected to other missions, and Voyager will drift on, alone, silent, into the dark, but not entirely alone. Attached to the side of each Voyager spacecraft is a golden record, a 12-inch gold-plated copper disc designed to survive in interstellar space for billions of years. It was the brainchild of Carl Sagan, who chaired the committee that selected its contents. The record contains 116 images encoded as analog signals, 90 minutes of music from around the world, greetings in 55 languages, and a selection of natural sounds: thunder, wind, surf, bird song, whale song, a mother's kiss, a baby's cry. The cover of the record includes diagrams showing how to play it, using a stylus and cartridge included with the disc. There's a diagram showing the spin rate, 16 2/3 revolutions per minute. There are instructions for decoding the images, which are stored as sequential scan lines. And there's a map showing the position of the Sun relative to 14 pulsars, rapidly spinning neutron stars that emit radio pulses at precise and unique frequencies. Any civilization advanced enough to intercept Voyager and decode the pulsar map could trace the probe back to its origin. The chances of anyone finding the golden record are essentially zero. Space is vast. Voyager is tiny. It emits no signal, no light, no heat. It's a dark piece of cold metal, less than a ton in mass, moving at 61,000 kilometers per hour through a galaxy containing hundreds of billions of stars separated by light years of emptiness. Even if another civilization exists somewhere in the Milky Way, even if they have the technology to detect objects the size of a small car at interstellar distances, they would need to be looking in exactly the right place at exactly the right time. The probability is not just low, it's negligible. But Sagan understood that the record wasn't really for aliens. It was for us. It was a statement about who we are and what we value. It was an act of hope, a declaration that human beings are the kind of creatures who send messages into the void even when no reply is expected. The record says, we existed. We had music and language and mathematics. We cared about beauty and knowledge. We looked up at the stars and wondered, and we tried to reach them. Voyager 1 is headed in the general direction of the constellation Ophiuchus. In about 40,000 years, it will pass within about 1.6 light-years of a star called AC plus 793888, a dim red dwarf in the constellation Camelopardalis. It won't stop. There's nothing to stop it. It will drift past, dark and silent, and continue deeper into the galaxy. In 1,000,000 years, it will be somewhere else entirely, surrounded by stars we cannot name. In 1 billion years, the Milky Way itself may have merged with the Andromeda galaxy, and Voyager will be drifting through a galaxy that looks nothing like the one it left. The golden record might survive all of this. Gold doesn't corrode. In the vacuum of space, protected from oxygen and water, the record can last for billions of years. Cosmic rays will gradually degrade the surface, pitting it with microscopic impacts, but the degradation is slow. The record might remain legible for 1 billion years or more. It is, potentially, one of the longest-lasting artifacts ever created by the human species. A message in a bottle thrown into an ocean of stars. Let's talk about what comes next, because Voyager's mission, remarkable as it has been, has also revealed how little we know about the space beyond the heliosphere. NASA has been studying concepts for an interstellar probe mission, a spacecraft designed from the ground up to study the heliosphere and the interstellar medium. Unlike Voyager, which was built to study planets and stumbled into interstellar space as an afterthought, the interstellar probe would have one primary goal: reach the heliopause as quickly as possible and study it in detail from multiple angles with modern instruments. Current design suggests the probe could reach the heliopause in 15 to 20 years, compared to Voyager's 35, using advanced propulsion systems. One option is a solar sail, a large, thin, reflective sheet that uses the pressure of sunlight for propulsion. By performing a close flyby of the Sun and deploying the sail at perihelion, the probe could achieve very high speeds using the intense solar radiation near the Sun's surface. Another option is nuclear electric propulsion, using a small nuclear reactor to power an ion engine that provides continuous low-thrust acceleration over years. The probe would carry far more advanced instruments than Voyager: better magnetometers, more sensitive particle detectors, plasma analyzers, cameras capable of imaging the heliosphere from the inside and outside, and communication systems based on laser technology rather than radio. Laser communication can transmit data at much higher rates over longer distances with less power, allowing the probe to send back more detailed information even as it moves farther from Earth. The interstellar probe would also address a fundamental limitation of Voyager's data. Voyager sampled the heliosphere at only 2 points, the locations where the 2 probes crossed the heliopause. We're trying to understand a 3-dimensional structure that spans billions of kilometers from just 2 data points. The interstellar probe, by choosing a trajectory carefully, could add a 3rd sampling point, and its improved instruments could gather far more data at that point than Voyager did. There are even more ambitious concepts on the drawing board. Breakthrough Starshot, a privately funded initiative announced in 2016, proposes sending thousands of tiny probes to nearby stars. Each probe would be about the size of a microchip, a few grams in mass, attached to a light sail about 4 meters across. A powerful ground-based laser array would push the sails, accelerating the probes to roughly 20% the speed of light. At that speed, the probes could reach Alpha Centauri, the nearest star system, in about 20 years. 20% of the speed of light, 60,000 kilometers per second. At that speed, you could travel from Earth to the Moon in about 6 seconds. From Earth to Mars in about 5 minutes. From Earth to Pluto in about 7 hours. From the Sun to the heliopause in about 3 days. The Starshot probes would cross the wall of fire so quickly that the superheated particles would barely have time to interact with them. But 20% of light speed creates its own problems. At that velocity, even a grain of dust carries the kinetic energy of a small bomb. A collision with a milligram particle at 60,000 kilometers per second would release energy comparable to a hand grenade detonation. The probes would need to be designed to survive these impacts, or more realistically, they would need to be sent in such large numbers that some losses are acceptable. Communication is another challenge. Each Starshot probe would carry a tiny laser transmitter powered by the same light sail that propelled it. The signal from a chip-sized transmitter at a distance of 4 light-years would be unimaginably faint. Detecting it would require enormous receiver arrays on Earth, far larger than anything currently built. And the data rate would be glacially slow, perhaps a few bits per second, making it impractical to send back large images or complex data sets. These challenges are real, but they're engineering challenges, not physics challenges. The laws of physics allow Starshot to work. The question is whether we can build the technology to make it practical, and that's a question that might be answered within our lifetimes. Now let's step back and think about what Voyager has taught us. Not just the specific scientific findings, the temperatures, the magnetic fields, the particle densities, but the deeper lessons about our place in the cosmos. The first lesson is about boundaries. We think of the solar system as having a clear edge. The textbooks show a neat sphere with the sun at the center and a clean line at the perimeter. Voyager showed us that the edge is messy. It's a transition zone, a region of chaos and mixing where two cosmic environments collide. The boundary is dynamic, shifting, breathing with the sun's activity cycle. It's not a wall, but a membrane, selectively permeable, allowing some things through while blocking others. The clean line in the textbook is a fiction. Reality is more complex, more interesting, and more beautiful. The second lesson is about protection. The heliosphere is a shield. It deflects cosmic rays, reduces radiation exposure in the inner solar system, and creates the relatively benign environment in which life on Earth has evolved. Without the heliosphere, cosmic ray flux at Earth would be significantly higher, with unknown but potentially serious consequences for the biosphere. We live inside a magnetic bubble inflated by our star, and that bubble is the reason we exist. It's an invisible, taken-for-granted form of protection, as essential to life as the atmosphere or the ozone layer. Every star has its own version of this bubble. Every stellar wind creates a boundary where it meets the interstellar medium. The size and strength of that boundary depend on the star's activity, the density of the surrounding medium, and the star's motion through the galaxy. A star with a strong wind and a favorable environment creates a large protective heliosphere. A star with a weak wind or a dense surrounding medium creates a small one, offering less protection to any planets within. This has implications for the search for habitable exoplanets. We usually define habitability in terms of temperature, looking for planets in the habitable zone where liquid water can exist on the surface. But temperature is only part of the equation. A planet might be in the habitable zone, but still be uninhabitable if its star's heliosphere is too small or too weak to shield it from cosmic rays. Voyager's data is helping scientists think about this additional criterion, adding a new dimension to our understanding of what makes a planet truly capable of supporting life. The third lesson is about scale. The solar system is vast. The distance from the Sun to the heliopause is about 120 astronomical units, roughly 18 billion kilometers. Light takes about 17 hours to cross it. Voyager took 35 years, and the solar system, enormous as it is a speck in the galaxy. The nearest star is 4.24 light-years away. The Milky Way is 100,000 light-years across. The observable universe is 93 billion light-years in diameter. Each step outward in scale reveals a new layer of emptiness, a new gulf of distance that makes the previous one seem trivial. Voyager is the farthest thing humanity has ever built. It's our longest reach into the cosmos, and after 47 years of continuous travel at 61,000 kilometers per hour, it's traveled about 0.006 light-years, less than 1,000th of the distance to the nearest star. In cosmic terms, Voyager hasn't even left the front porch. The journey to the stars, if we ever make it, will require speeds and technologies that are currently beyond our reach. The fourth lesson is about time. Voyager was built in the 1970s with 1970s technology. Its computers have 69 kilobytes of memory. Its transmitter runs on 23 watts. Its cameras, state-of-the-art in 1977, would be outperformed by any modern smartphone. And yet, this 47-year-old machine is still functioning, still returning data from a place no other instrument can reach, still teaching us things we didn't know. The mission was supposed to last 5 years. It's lasted nearly 50. The engineers who designed it are retired or dead. The code that runs it was written in languages that are no longer widely used, and yet it works. It works because it was built with care, with redundancy, with attention to reliability over cleverness. There's a lesson in that. In a culture obsessed with the latest and fastest, Voyager reminds us that durability matters, that the best technology isn't always the newest, but the most reliable. And the fifth lesson, perhaps the deepest, is about what it means to explore. Voyager wasn't sent to find anything in particular beyond Jupiter and Saturn. It was sent to look, to measure, to report back. The discoveries it made at the heliopause were unplanned, unexpected, and in many cases contradicted the prevailing theories. The magnetic highway, the aligned magnetic fields, the temperature extremes, none of these were predicted. They were found because someone decided to keep looking, keep listening, keep a 47-year-old machine running, just in case it had something else to tell us. And it did. Exploration is not about knowing what you'll find. It's about being willing to find things you didn't expect. Voyager embodies this principle more completely than perhaps any other scientific mission in history. It was built to study 2 planets. It ended up mapping the edge of the solar system and sending back data from interstellar space. The greatest discoveries are often the ones you weren't looking for. Right now, as you're listening to this, Voyager 1 is receding from Earth at about 17 kilometers per second. Every second, it's 17 kilometers farther away. Every minute, 1,000 kilometers. Every hour, 61,000 kilometers. Every day, 1.5 million kilometers. By the time you wake up tomorrow, Voyager will be 1.5 million kilometers farther from Earth than it is right now. Its signal, 23 watts of radio power broadcast through a 3.7-meter antenna, takes 22 hours and 35 minutes to reach Earth. By the time the signal arrives, it has spread out over a sphere with a radius of 22 light hours, covering an area of trillions of square kilometers. The power density at Earth's surface is about 10 to the minus 25th watts per square meter. That is unimaginably faint. To detect it, NASA uses the Deep Space Network, 3 facilities located roughly 120 degrees apart around the globe, in Goldstone, California, near Madrid, Spain, and near Canberra, Australia, so that at least one antenna can always see any point in the sky. Each facility has a 70-meter dish antenna, one of the largest steerable radio antennas on Earth, which collects the faint whisper of Voyager's signal and amplifies it for analysis. Even with these enormous antennas, the data rate from Voyager 1 is about 160 bits per second. That's roughly 20 bytes per second, slow enough that downloading a single smartphone photo would take about a day. Slow enough that a single high-resolution image from Voyager's cameras, back when they were still working, took hours to transmit. But it works for now, and every bit of data is precious. Voyager 1 will go silent within the next few years. Maybe 2025, maybe 2030. The exact date depends on how aggressively NASA manages the remaining power and how long the aging components continue to function. When the power drops below the minimum threshold for the transmitter, the signal will stop. The Deep Space Network will listen for a while, hoping for a miracle. Then it will move on, and Voyager will drift on, silent, dark, cold, moving at 17 kilometers per second through the interstellar medium, carried by its own momentum, subject to no force except the feeble gravity of distant stars and the even feebler drag of interstellar gas. It will not slow down appreciably for millions of years. It will not stop for billions. It will orbit the center of the Milky Way along with everything else, completing one galactic orbit every 225 million years, a journey it will make dozens of times before the Sun dies. In 40,000 years, it will pass within 1.6 light-years of AC plus 793888, a dim red dwarf. It won't stop. There's nothing to make it stop. It will continue on, tracing its path through the galaxy, a dark, silent artifact of a species that existed briefly on the third planet of an ordinary yellow star. In 300,000 years, Voyager 1 will have traveled about 5 light-years from the Sun, far enough to have passed several stellar systems, though probably none close enough for any meaningful interaction. In a million years, it will be about 17 light-years away, still within the solar neighborhood, still drifting through the same arm of the Milky Way. In 10 million years, about 170 light-years. In 100 million years, about 1700 light-years. Still inside the Milky Way, still drifting, still carrying the golden record. The golden record is designed to last. The gold plating protects the copper substrate from corrosion, though in the vacuum of space, corrosion in the chemical sense doesn't happen. The primary degradation mechanism is cosmic ray bombardment, high-energy particles that gradually damage the surface at the atomic level. But the rate of damage is slow. Estimates suggest the record could remain largely intact and readable for 1 billion years, possibly longer. 1 billion years, try to hold that number in your mind. 1 billion years ago, life on Earth was exclusively microbial. Multicellular organisms didn't exist. The continents were in different positions. The atmosphere had a different composition. 1 billion years from now, the Sun will be about 10% more luminous than it is today, hot enough to have evaporated Earth's oceans and rendered the surface uninhabitable. Humanity, if it still exists in any form, will be somewhere else, or it will be gone. But the golden record will still be out there drifting, carrying its cargo of sounds and images and music. Bach's Brandenburg Concerto No. 2, Chuck Berry's Johnny Be Good, a Navajo night chant, a Pygmy girl's initiation song, greetings in 55 languages, including a message in Sumerian, a language that hasn't been spoken in 4,000 years, the sound of a human heartbeat, the sound of a kiss. All of it encoded in the grooves of a gold-plated copper disc, sailing through the galaxy at 17 kilometers per second, waiting for someone to find it and figure out how to play it. The odds are essentially zero. But the record exists, and as long as it exists, it carries a piece of us with it, not just information about Earth, but something harder to define. An intention, a hope, a refusal to accept that we are alone and that our existence doesn't matter. Carl Sagan wrote about Voyager and the Golden Record with a clarity and beauty that is difficult to surpass. In Pale Blue Dot, he described the famous photograph that Voyager 1 took of Earth from 6 billion kilometers, a single pixel of light in a scattered sunbeam. He wrote about the smallness of Earth, the fragility of it, the importance of treating it and each other with care. He wrote about the cosmic perspective, the view from far enough away that all of human history, all of our triumphs and failures, all of our wars and loves and discoveries, shrinks to a point of light barely visible against the dark. That perspective is Voyager's greatest gift. Not the data about magnetic fields and particle densities, though that data is invaluable, but the perspective, the reminder that we are small, that the universe is large, that the distances between stars are so vast that crossing them may take centuries or millennia, if it's possible at all, and that despite all of this, we tried. We built a machine, we hurled it into the void, and we listened for its signal for half a century. We sent our music and our voices and our hopes into the darkness, not because we expected an answer, but because sending them was important. Voyager 1 is 15 billion miles from home. Its power is fading. Its systems are failing. Its signal is growing weaker every year. Within the next few years, it will go silent, and we will lose contact with the farthest thing we've ever built. But it won't stop. It will keep going. Past the stars we can name, past the stars we can't, through regions of the galaxy we've never seen, for millions of years, for billions, carrying the golden record, carrying our message, carrying, in a sense, us. There are billions of stars in the Milky Way, trillions of planets, and somewhere among them, drifting quietly through the dark, is a small machine made of aluminum and gold and plutonium, built by a species that existed for a few 100,000 years on a planet that will one day be swallowed by its dying star. The machine carries a record. The record carries a message. The message says we were here. We looked up, we tried, and somewhere out there, far beyond anything we can see or reach or imagine, the galaxy continues. Stars are born, stars die. New planets form from the debris, and perhaps on one of those planets, billions of years from now, something will look up at its own sky and wonder if it's alone. It isn't. We sent a message. It's on its way.